Answers to the questions set for section C7.4. Gapful exercise. I'll just let you pause the video there and you can mark those. This is just shorthand for positive and shorthand for negative to avoid confusion. Next page, if we're looking at question 1, they ask if, in each case, if the reaction is exothermic or endothermic. You calculate this by putting a positive value for the energy required to break the bonds in the reactants and a negative value for the energy that is released when new bonds are formed. The difference between those two, if it is negative, it's exothermic, and if it is positive, as in B, it's endothermic. Okay, and C is also exothermic. Question 2. So in A, they ask you to break down the types of bonds and number of those bonds that need to be broken, their energy, their combined energy, so that is a positive figure, the bonds that are made and the number, and substituting their values. All these values are from the table here, giving us a total. This is the energy required to break the bonds, energy released when new bonds are formed. The overall energy change is -6, so it is exothermic. Okay, question 3. They ask you to fill in each table. So bonds that are broken, bonds that are formed, the total energy for both of those, and the overall energy change, which is another exothermic reaction. Okay, this one we have to produce our own table on each side. So I've used the left-hand side for bonds broken, which gives us a total of 3758, and bonds formed, which is -5072, and the overall energy change is -1314 kilojoules per mole. Remember your units. Okay, question 5. We'll come to this reaction in more detail later on next year. This is the Haber process. You'll need to know it well. 3 hydrogen molecules react with 1 nitrogen molecule to form 2 ammonia molecules. It's a reversible reaction. You don't need to put that in at this stage, but I thought I'd add it anyway. Number and type of bonds to be broken, and number and type of bonds that are formed. The energy required to break all those bonds, followed by the energy released when new bonds are formed. The overall energy change, taken one from the other, so it's exothermic, and an energy level diagram here to show us what's happening. So because this is exothermic, the reactants level is always higher than the products level. So make sure exothermic, these are this way round. Show the activation energy here. Just draw dots along from the line from the reactants across and then up to the top of that curve. And then the difference between the two levels of reactants and products is your delta H value, -93. So we've used the information from our calculations to label the diagram. Okay. Question 6a. Draw out the molecules. Again, hydrocarbon molecules, we've not had a lot to do with these, and we'll come into these in more detail later on in the course. Bromine molecule reacts with it, and it forms this molecule and HBr. Okay, so this is bromoethane and hydrogen bromide. This is ethane and bromine. Write out the bonds that have to be broken to convert the reactants, which we've got there. And then you have to put the values in. Now, I couldn't find the values for bromine in the booklet, so I looked those up. Okay, so apologies there on behalf of the science department. Gives us a value here for bonds broken, 606. And again, these bonds we had to look up, and it gives us minus 647. Okay. F, calculate the overall energy change. It's exothermic. And write the enthalpy change with the correct sign, including the units. Delta H is your enthalpy change, minus 41 kilojoules per mole. Okay, so on this section, rather than draw all of these out, I calculated the energy changes for the following reactions. So the overall energy changes minus 185, minus 486, minus 1856, minus 816. These three here didn't have enough room, so what I've done, I've put the answers in here, and the last two I've just written out longhand for you, so you can have a look at these. So this is how we draw ethene reacting with hydrogen to make ethane. And we are breaking a carbon-carbon double bond and a hydrogen-hydrogen bond. And we are forming two new carbon-hydrogen bonds. So if we want to see where these are, that bond is going to be broken. That bond is going to be broken. And the two new bonds that are formed are here and here. Okay. So we put the values in. It gives us an endothermic reaction, 222 kilojoules per mole. This molecule here is ethanol, and it produces ethene and water. The bonds that are broken are CH and CO. So this bond is broken, and this bond is broken. And the bonds that are formed are carbon-carbon double bond and one OH bond. It's only one because we've got one here already. We're just adding another hydrogen on here. Overall energy changes for each, and then your delta H value, minus 305, exothermic. Okay, question 8. We're nearly there. Calculate the bond energy for iodine given the following data. So what I've done here, I've written the whole thing out. Hydrogen plus iodine reacts to give hydrogen iodide. Overall energy change is minus 9. So we substitute in the values from the table. Hydrogen bond energy value is 436. We don't know the one for iodine. 2 lots of 298 equals minus 9. So let's start tidying this up. 436 plus the bond value for iodine gives us minus 596 gives us minus 9 overall. Rearrange the equation and it should give us plus 151. Okay. Student follow-up questions. We've already calculated this one before. Answers there, and your energy profile is there. State the advantage and disadvantage of hydrogen as a fuel. It produces water as the product, so it's very low pollution. It produces a lot of energy as well per gram, but it's very reactive and it's difficult to store. Question 1 here at the bottom is repeated from question 6. So I think the rest of it is all question 6. Okay, so we've done that already. So it's just repeated. All right, I hope that's been helpful.